the problem that Thibault is working on is, can we formally prove mathematical formulas automatically? This is the dream of the AITP, I guess, or at least one of them. And his approach, I'll go through this slide in a bit of detail. This is basically the architecture of the system that Thibault has developed. It's called Thibault. And this is also the plan for what we're going to talk about in this talk. So there are two aspects to Thibault. There's a supervised learning problem, and then there's the actual theorem proving side of the system. So the supervised learning problem is given a corpus, which we call this formal library of statements and their proofs in some interactive theorem proving system. So we're using the whole theorem prover. We can learn by doing proof recording. We can learn which proof methods are suitable for use in a particular conjecture or for a particular goal state. So in the middle of your proof, you can pretend that you're the human who's doing the next step of the proof, and during proof recording, you learn, okay, at this step, this kind of proof states, I should try to apply this kind of step. So Thibault does proof recording over a large corpus of human written proofs and stores all this information in a knowledge base. And then from the knowledge base, we produce some predictors, which are basically machine learned functions that, given the proof state, predict what should be the next tactic that's applied at that point. And there also are a few little steps of improving the quality of the knowledge base that can be done offline to make it better for producing better predictors. Okay, so that's the supervised learning part. And then the predictors are what's used in doing the proving. So this is the traditional ITP proving approach. You start with your conjecture, and then you need to apply some tactics. And if you're doing it automatically, as we are trying to do, then you need a search tree and a search policy for searching through the possible tactics that you might apply at any point during your proof. And so they use the predictors to come up both with the tactic policy, which is given your state what tactic to choose, and also the tactic evaluation. So there's a predictor which says, at this proof state, how likely is it that or how far away am I from a solved state? So it's kind of giving you a value estimate of where you are in the proof. Okay, so that's the main bulk of Thibault, is doing this proof search to find the proof. And then once you've found the proof, you also want to minimize it and clean it up and make it a nice human readable proof that you would want to then put into your file again. And then you get your proof. So that's the system. And so for the first part of the talk, I'll give you some basic overview of ITP and also a demo of Thibault in progress to see like what it actually looks like, that it's usable. And then Thibault will take over and give the rest of the talk, which is explaining how he does it, like how do we actually do the proof recording and the training and the predictors and the proof search. So first, some introduction to reasoning in ITPs. I know many of you will be very familiar with this, but for the few of you who aren't, then it's a bit helpful, and for those who are familiar, maybe it's a good revision. So basically the idea is this blue dot here represents the statement that we're trying to prove. These green dots might represent axioms in our system, or they might represent previously proved theorems. And what is shown on this slide is the very traditional forward proof mode. This is the way you might think as a logician, is that you start from your axioms, you apply some inference rules, you get some intermediate states, apply some more inference rules, finally you get to a state which is the one that you want. So this is the logician's view of how to do a proof, but from an interactive theorem prover person's view of how to do proofs, we prefer to do them backwards. It's more like a game. Here you instead start from your conjecture. So this is what I want to prove, and the arrows are now not going to be inference rules, but rather tactics, which manipulate your conjecture. So you can think of it as an initial proof state. They manipulate your proof state to give you some more proof states. So these, we call them sub-goals. And your sub-goal might be already a theorem that exists, or it might be some trivial axiom, so then you're done, you don't need to do any more proof. Or it might be some intermediate state, which is a goal, and you apply another tactic and eventually reduce everything to things that you already know. So this is called backwards proof. And this is the way that people write big proofs in interactive theorem provers. They always start with a conjecture, a big conjecture, and then reduce it via tactics to do backward proof back to the beginning. And this is the thing that we're trying to automate with tactic toe. So take the human out of having to decide which arrows to put here, and instead have the machine figure them out. So what do tactics look like? So we're in the whole 4 theorem prover. We've also seen previously some work on whole light. These are very similar theorem provers that have tactics with similar names. Here are some examples. So you have like individual tactics, so rewrite tac takes some theorems and applies rewriting across your goal, or induct tac will take a goal of a particular shape and turn it into an induction, like do this, set up the induction for you. Or metis tac, which is an embedded first order theorem prover, which will take a proof state that's essentially first order and run a decision procedure on that, or like a first order prover. The tactic language in which you write these proofs, it has those tactics as the atomic kind of steps that you can take. But then to write a full proof, you use usually more than one tactic at a time, and they are combined with so-called tacticals. So then L is one of them. This means apply this tactic, and then given, so say apply induct tac, it might produce you then 2 sub-goals, one for the base case and one for the inductive case. And then you can stick the 2 things that you're supposed to do after that together with a then L to get a complete proof, like this. So induct tac, then L, regex this tac. And there's then L is one example, but I tend to use other combinators like then one, whatever. So that's what a complete proof might look like. Okay, so now let's jump to the demo to see what it really looks like in the whole theorem prover. So this is first of all what the whole theorem prover looks like. So I've got on the left here an ML real print loop, but it's also augmented with like the ability to store theorems and manipulate theorems. I can take a variable and produce the theorem that they're equal. But the way you usually use such a system is you set up a goal. Like here's a nice goal about some properties about lists. So it's kind of yeah. So here I'm saying if I've got as assumptions that X is an element of this list, LS, and also if I map F1 over LS, it's equal to mapping F2 over LS, then I would like to demonstrate that F1 applied to X should be equal to F2 applied to X. So this is a fairly straightforward fact that you might, and so if I'm just proving it myself as an expert user of Hall 4, I would say, so I'm over here now, this is my tactical proof, I might say, okay, let's rewrite the goal to put it in a nicer form. Okay, what's going on? I know that these map holes, so I'm going to pull out, well, I know if these lists are equal, then I should be able to say that their elements are equal. What does that do? Then I want to simplify away L map. So you might do some stuff like this, and then say, okay, so I've got that the elements of LS are equal under F1 and F2, as long as it's less than length, and I know that's basically what mem means. So I'm going to use the theorem that I know about mem to prove that. So I've been doing rewriting and using theorems that are coming out of my head. But for someone who hasn't programmed in Hall 4 before, this is like total magic, or at least would require several months of learning. Luckily, we can instead run tactic toe first to record every proof in the Hall 4 standard library, and thereby do its own learning about how these proofs should go. That takes, about 2 hours, as opposed to several months for a human. And then we go back to my initial goal and run this magic tactic toe tactic. And then it says, okay, I found a proof. And it actually found a much shorter, simpler proof than me. It's just rewriting with this one theorem, map EQF, which I thought about. So I can copy that proof exactly and run that, and that will solve it. Or, I can use the fact that it found that theorem for me and just use my own tactic to solve it. So that's one nice example. And the other good thing about it is you can use it on proofs in many different domains, because so here's a theorem about sets. So it's saying this one's a bit less obvious to know why it's true. So this count here means all of the numbers up to n plus n. So if I take the set of those numbers and take away the set of numbers which are just up to n, that should be the same as taking numbers up to m and then adding n to all of them. So taking the image and adding n to all of them. So this theorem, I don't know how I would approach it, but probably an extension to do some logical formula. But even at this point, I don't really want to think about what's going on here. So I will instead just call tactic toe. And it finds quite a long and interesting proof, so I'll just copy that through. And we can look at what it's done. So Tactic-Toe has done quite a lot more than other systems you might have seen, like Polyhammer and basically calling out to metastack or something like this, in that, yes, it does some rewriting first, but now we in an intermediate proof state, we have to come up with this existential witness, and Tactic-Toe actually, says, okay, in this type of goal, I want to call exist tag to provide the witness, and it also synthesizes the witness, and then does more rewriting to finish the proof off. So it's quite powerful. Does anyone have any requests or theorems you want to try Tactic-Toe on? I'll happily take one, and then I'll move on to the rest of the talk. If not, I can show another example.
Something with induction?
Yeah, something that doesn't touch it is a good idea.
Partial value induction.
What's that?
Partial value induction.
From ordinary induction, yeah, that would be a nice challenge.
Yeah, that would be hard for me to write down very quickly. So maybe we need to come up with like induction test theorem, which will be something like, I don't know, for all lists, if you, yeah?
Associative property of these concatenations. Okay.
Yeah, sure. So,
Yes.
the only problem with this is it's probably already.
Yeah.
But we could try to do it like a more generalized version, which has, maybe several lists. Alright, so this is like doing some associativity reasoning on. So rewriting the associativity of these lists. If I run Tactic-Toe on that, hopefully come back with something good. Yes, it immediately says metastack with appendix.
That makes sense.
Yeah, so it's pretty good. We can do more demos at the end if you want. Let's go back to the talk. So now Thibault will explain how this is possible.
Okay. So let's try to start with the proof recording. So I will have one slide on this, but this is the thing that takes the most time to do. So you start with proof. In this proof, I omit the arguments of the tactics, but normally there are arguments there. And then you wrap the proof around with a recording function, R. And this recording function is recording what goals are passed to the tactic, and record the tactic together with the goal, creating a goal tactic pair. So you see at the end you have a list of pairs where you have like a goal here and an associated tactic, a goal there, associated tactic, and so on. What you have to do, which is also a lot of work, is to generalize globalize the names. Here you see you have just induct tag. You have to prefix by the modules where they appear, so that you can reuse any these tactic strings in any part of the libraries. So everything is recorded as strings and then reparsed into O4 afterwards. So that's how the database of tactics is constructed. So let's now switch to the predictors. So you have predictors, and then we will derive the policy and the evaluation. So predictor is just the nearest neighbor algorithm with weighted TF-IDF heuristics, which weights symbols using the rarity of the symbol. So if you have a rare symbol, it's likely more important and has more information. What the effect is that it order goals from the database according to a distance to a target goal. So you might think this is just premise selection. How can we predict tactics with this? So let's see now how we do the tactic policy. So I copied the database here, and the database of tactic is actually a map from goals to tactic. So if you order a list of goals, you can infer an order on tactics from that. So that's our policy here. Let's say we have a new goal here, and then from this new goal, we look at all the goals that are close to this goal according to the nearest neighbor distance, and we calculate a rank. And this is the tactic. For example, rewrite tac is the first prediction, so it's the best one for this goal. And after that, we need a policy between 0 and 1. So here I just take 1 over 2 to the power of the rank. But there are other possible functions for this, and you can also try to learn it. So now for the value. So we need also a value to evaluate the output of tactics. So like the tactics will produce goals, and we want to evaluate how likely that these goals are provable. And what is interesting here is that it's different from ATPs. When a tactic produces goals, all the goals are independent from each other. So you can evaluate them independently because they are. You can estimate how good, if they are provable, and how many steps it takes to prove them. So for now, we just have positive examples from human proofs, negative example from searches of tactic code, and we just calculate the ratio of positive example over in the 10 closest list of goals. So it gives you the value function. In future work, we would like to estimate not the probability, but the time it takes to prove the goal, which would be much more effective than just the probability, because something can be provable, but it would take a long time to prove it, so it's not useful. Also, you could do backward steps. You could have like something provable and you expand it, and it's still provable, but it's not going in the right direction. So it would be better if you have this number of steps as a value function. So now we have the policy and the value. We can now construct the search, but before constructing the search, I will talk about the training, how we can improve the database. So training will have 3 training steps. The first one is called orthogonalization. So what we do the training to improve the recorded data. So and that creates better prediction algorithm. And we start with the orthogonalization steps. So what was the issue here? We have many tactics that do the same thing. So from the same goal, they produce the same output. So it's really not good to try them again and again. If they fail, or even if they succeed, then you just split your proof again. Or yeah, there's some mechanism to avoid that, but still we don't want to even try to apply them. So the solution is if we have a new goal that we want to insert in the database, a goal tactic pair, we don't insert it directly. We just make a competition among all the tactics that already existed, and we see which one is the most has the same as the best effect and is the most popular. So let's say we have this goal tactic pair we just recorded, and there's induct tac here, but we may not want to record that induct tac can solve this goal. We may want to record a more general tactic instead. So we look at which tactic make progress on this goal, and we see that rewrite tag doesn't make progress and method tag does make progress. And then among the tactics that make progress, we look at the coverage. And if the coverage is higher, we take the one which has highest coverage, and instead of adding index tag to the database for this goal, we add then method tag, because method tag has higher coverage. So in this way, we just try to limit the number of tactics that we can use during the proof search. And it provides 6% improvement in the final results. So let's see even better idea. So for now, we didn't think about arguments of tactics, but now let's try to think of them, because we had a problem like if theorem never appeared in any tactics in before, but still was created, then we could not predict it. So we would like to predict theorems also independently of tactics. So the solution is to abstract tactics that contains theorems in abstract them and then instantiate them during the proof search. And the instantiation is doing premise selection and is looking at the current goal. So here is an abstraction algorithm. So let's say we have rewrite tag and we have two theorems here. We will just replace it by a variable, and then at runtime we decide, depending on the goal, which a list of theorems to instantiate X with. So it's very important to be a list of theorems, because then we can make errors. So because rewrite tag is quite resilient. So if you add a theorem that does nothing, it doesn't fail. So you can predict, like we usually predict 16 theorems here. And if this 16 theorems contains T1 and T2, maybe it does make more progress than the original tactic. So it will be selected during orthogonalization. So we let them compete during orthogonalization. So, and the last step of the training, which is not really a step for training, is just a step just before you try to prove a new goal, a conjecture. You will try to optimize the prediction a bit. So, because we have an issue that the predictions, they are too slow during proof search. So if you have the full database, maybe you have like maybe 100,000 tactics to choose from. We only preselect 1,000 suitable tactics, and we use dependencies, which is, for example, dependency can be if a tactic is selected and there's another tactic in the same proof, but we can say we also select the other tactic. And this is really, now this is not for this. This 15% improvement is for the abstraction algorithm, when you add premise selection to tactic selection. And pre-selection is a requirement to run the algorithm, otherwise you cannot even start to run it. Now we discuss the proof search. So you see it's an advanced proof search with policy and an evaluation. So first let's just describe what the search tree looks like. So we have like a list for each node here. We have a list of goals that are to be proven, and from each goal we try many tactics. So here all the goals have to be proven. So it's a conjunction, but if here it's a disjunction of tactics. You can try one tactic. If one of the tactics succeed on this goal, then the goal is solved. And each tactic produces a list of goals. So in the next example, we will only consider nodes that contains only one goal for simplification of the presentation. And this is just how we see how the policy and the evaluation works. So we start with the conjecture here at the bottom. And then we have the policy function here. It's a prior policy. So since the prior policy is higher here, we choose this one. You apply this tactic, and it produces a list of goals. And then we evaluate the list of goals here, which is just one goal in this example. And we also make the create the next prior policy for this goal. And we backpropagate the evaluation. We do it again. So starting from here, let's say 0.7 was not too bad, so we go again this way, and now we choose 0.5. So this time the evaluation is worse, so it's 0.3. So we added this evaluation back to this node. So now the evaluation of this node is the average of these two, and so it's 0.5, and the evaluation of this node is 0.5. We do now the evaluation is too bad maybe, so we choose the next one, or we have explored it too much. The number of visits was too high, so we have a new evaluation, and it continues like this. This is the final evaluation for Hoggle, and we solve the. So in this case, we solve the proof search if there is one tactic that doesn't produce any new goal. So if there's a path in this tree where when you apply the tactic, it doesn't produce any new goal. So now the results. We evaluate it by reproving the library. So I would say it's kind of fair, but Frank may not agree. It states that only previous proofs are available for training, but the reason it's not totally fair is because the library has already been refactored by humans. So the order of theorems are already in a good order. So it helps quite a lot. Another point for fairness is that in this evaluation, we don't allow tactic to call any external provers, although this is possible. So because we want to compare tactic with other prover like eProver, and we do the evaluation on all four. We evaluated 7,000 theorems for 60 seconds each, and this is the results. So we get very big improvement over eProver, and also, and if you combine the two, you can even get to 69% of theorems, top level theorems, so theorems that are named in the library, reproven. We did also a short evaluation on KKML, only on 2/3 of the library, where we have 3,000 theorems, and we could reprove about a bit more than 1/3 of them. Yes?
Does this correspond to the last year's Cask LTB problems, or is it a different version of the problem?
Yes.
Okay.
Also, I didn't put eProver there because when I provided the dataset for eProver, it was missing some theorems. Although I don't think it would change much. I think eProver could do 20% if he had the right eProver had the right dataset. But I didn't want to put numbers I was not sure about. Let's see now a bit more details about the results, because this just percentage, it doesn't tell us much. So how the library looks like. Are there long proofs in the library, or only short proofs? Or what is the distribution of the proofs? So this is the length of the proof in terms of number of tactics here, in the y-axis, in the x-axis, sorry. And in the y-axis is the number of proofs that have this length. So there are, like, in all four libraries, there are 2,000 proofs that have length 1, and about 500 proofs in the KKML libraries that have length 1. And now I have, if I want to go, so it goes down very fast until 15, so I have to rescale it, otherwise you don't see anything anymore. So in red is all for the human proofs. In this is the human proof, and dashed are the distribution proofs formed by tactic-toe. So it means that the proofs formed by tactic-toe are much shorter than the human proofs, but it doesn't mean that it doesn't tell us anything about how good tactic-toe is. It could, for example, equivalent proofs are just one step always because they just call metastack. So let's see now how good it is relative to the amount of time. How does it scale compared to eProver in all 4? So this is after 15 seconds, it's like maybe 90% of what it can do in 60 seconds, but this maybe have some improvements still possible by running it longer. And for eProver, it's about half.
Which options do you use for E?
Auto schedule.
And do you tell it that will solve after 60 seconds?
Yes.
Okay.
You expect another graph
I
here?
expect another more humps later. Maybe they are too small.
Maybe here.
There is a hump at 45.
Yeah, also here maybe.
Maybe.
It's too small maybe.
Okay.
So I think that's a different strategy for eProver.
Yeah.
And we don't have any different strategy for tactic-toe, so it's pretty smooth. Now we will go for something more interesting. We'll try to evaluate tactic-toe and eProver relative to the length of the original proofs. So here, if you have a proof of size 1, originally, tactic-toe can find it 90% of the time. And if it's of size 10, then it's like 30% of the time, and if it's size 20, it's like 10% of the time. And sometimes it's lucky and it can find a proof of size 30 or 40, but usually it's, 10 is kind of maximum. Well, you can see this, there's still some proofs there. Yeah, so I will just show now just the minimization algorithm rapidly. So like that's the output of tactic-toe, the raw output, and there is a lot of there are module names, there are a lot of artifacts that comes from the recording, like this allkernel.quote. So we actually prettify everything to it's good for the user, so you can include this directly in the proof, and it doesn't have to rewrite so much from there to here. Also, it's doing a bit of minimization, which is really interesting. It's removing some steps that are unnecessary. The first step is not necessary, and it's minimizing the number of theorems in arguments. So if you have multiple theorems, but it's minimizing any list of argument. Actually, it's pretty general. It just provides a tactic again with a list a bit smaller, and if it succeeds, then it's just replace it by the smaller list, because it means that the argument in the list was not necessary. Okay, so I'll just conclude now. So we have a tactic-toe learns from human proofs to solve new goals, and it has many advantages over ATPs, especially for ITP users. So because it includes domain-specific automation that were done by clever developer of all4, for example, and it can generate the proof at the human level, so you don't need any translation to first order or reconstruction afterwards from the proof. That's very lot of advantages. So just for future works, I have 3 ideas. I want to enlarge the action space, so I already did some experiments with term prediction, more term prediction. Also, I would like to be able to, if you have multiple tactics that always appear together, maybe create a new tactic create a new function for it and give it a name. So you have to detect which tactics appear in a sequence, and that's worked on in Sepia, for example. And I also would like to learn from forward proofs. Also, I would like to train tactics more. Like in auto-organization, we train tactics because we tried new tactics on other goals that they were not supposed to be applied to. But I want to do this more and maybe get feedback from a good evaluation function, so I can get directly. I can just evaluate my tactic locally. I don't need to do a proof anymore. I just have a good evaluation function, and I just have a goal, apply the tactic to it, and then see if the output is good or not. And then related to the forward proofs, I would like to be able to conjecture intermediate lemmas so that you can prove, do longer proofs than steps, or longer. You can find longer proof because sometimes you need to conjecture some lemmas and so that splits the proof into two. So it's two, it's an exponential speed up if you do it rightly, but correctly. But the conjecturing is hard part. You have to have kind of a lot of ideas for this. So I have some, but this is not for this talk. Good, thanks.
Do you have heuristics for unfolding definitions? For example, a real number, you will hardly ever need that it is basically a dedicated code, if you set it up that way. But for a prime number, you will need that it is bigger than 1. So that property should be unfolded.
Mm-hmm.
And I think
there's almost no heuristic. The only heuristic I'm using is the nearest neighbor algorithm. So maybe you can deduce from the information. So I didn't talk about the features of so I'm looking at the goal and look at the feature of the goal. So the features could be subterms or constants appearing in the goal. And from these constants and features, I looked at what I've done before with these features and try to redo the same thing. So if someone has unfolded a real number before, I can learn from this. Or if someone has, if you should never unfold real numbers, then I can also learn not to unfold.
okay, so you do have that.
Yes, but not by heuristics. It's learned from supervised learning.
For that. It's not specially purpose for that particular
Yes.
case.
But I think it's an important issue, so.
Yeah, it just happens in the algorithm. The rewrite tactic, it happens because it's learned from human proofs. So it's if human proofs have done it correctly before, then it will reproduce the correct behavior.
So I see on your high-level graph you had the backward arrow from the proof that you have created. So that I saw that in England training is like you are training on the proof that are improved over the human proofs.
It's doing very minimal reinforcement learning. Like it could, you can train from the human proofs or for the.
So I mean, it's like to find a better proof than do you have to do a training set to train?
Yes. I did that, but it didn't improved by 1% or 2% the results. So I didn't include in the final version. So, but it's working a bit.
Yeah, about evaluation. So I remember that in the 90s there were already research and analogy in theory proving. In particular, in Alan Bundy's group, there was John Whittle doing a PhD, and there's an article in Journal of Automated Reasoning titled "Analogy in Inductive Theorem Proving." I was reminded on the paper when I saw the demo here. So So maybe you can have a look at the examples they probably had just a couple at a time and see whether you now, at least be able to do those and more robustly and so on.
Yeah. Well, seeing the next talk may also be quite relevant there. So I think I've time for one or two more.
I just when you were showing the graphs, like comparing the human proof with the tactical proof, and you talk about the number of calls or about the length of the proof,
Yes.
it seems to me that maybe you might, as an alternative metric, use the number of kernel inferences, because it seems to me that it's unclear, like one tactic can be Mattis, which is some crazy
I have some information about that.
Okay.
But it's not about the number of kernel inferences. I'm just replaying the proof and timing it, which is about the same as counting the number of kernel inferences. And I can compare the speed of the two produced proofs, the human proofs, and sometimes half of the time the tactical proof is faster, and half of the time the human proof is faster. So for half of the proofs, you may want to replace it by the tactical proof to make all four faster.
One last point from Ramana.
I know it's a weird question to my input, but I was inspired by your earlier question on whether it can do an induction. And so what I just did, some of you might have seen, is I defined my new append function, which tactic2 has never seen before. It's just called my app on lists. This is the standard definition. And then I said, okay, proof that this is associative. And honestly, I was expecting it to fail, but it found a proof. And the proof it found is induct on L1 and then metastack with the definition. And this definition is the theorem that it hasn't seen before either. So, well done.
Well, some of the previous questions and discussions gave a very nice lead into the next talk, because Alasdair was talking about indeed reasoning by analogy.
Okay, so I'm here to talk to you about automation by analogy in call. So this is based on the Machine Learning for Proof General tool. The Machine Learning for Proof General is a tool that interfaces with Proof General to extract features of lemmas from an interactive view improver such as COP and then cluster them. Proof General, for those who don't know, is a front end for interactive view improvers, and it's mainly used for COP nowadays. One important thing to remember with our feature extraction is that we do our feature extraction on proof terms. And we do this because if you had two proofs on tactics, for example, which is something like intro is a variable, rewrite, and then trivial, that rewrite can be completely different. And by using the proof terms, it gets the structure for them better and would then not put them in the same cluster. So the way we currently do clustering is that we link to either Weka or MATLAB, and then we have multiple algorithms such as k-means, Gautier, maximization, etc. And you'll get some learning looks like this, and then hopefully the lemmas will be in some n-dimensional space, and then you'll get these clusters of them together. For the purpose of this talk, I am just using k-means clustering to get the clusters. So if you're wanting to actually use MLPG currently, what you'd have to do is you'd be proving your interactive your improving file as normal, and then you maybe get to prove that you're unsure of how to solve, and then you can extract the clusters up to that point and ask MLPG to prompt you with similar lemmas. And then what you have to do is look at those lemmas and see if they're useful to you yourself. So here's an example I've got. So let's say you're trying to prove this lemma M3-3B. So there's an experimental file that we wrote, so the names are a little bit iffy, I'm sorry for that, but it's just basically a file that has a lot of similar kind of statements and proofs maybe use like different types of tactics and methods to see if it actually is clustering together properly. And basically we would see that this is similar to these two above. I just put them above, but they weren't there in the file originally. And you would then look at maybe M1 corrected, and if you could just copy and paste the proofs and see if it works. So you could try that and it doesn't work. M1 corrected wasn't what you're looking for, but if you actually copy and paste the proof for and B false R, you will get a proof. But that will actually also work. But a human might do something like look at this goal here and see that's very similar to and B false R, and then maybe write this proof instead, where you rewrite on and B false R and get trivial. So while it's been shown that obviously that you could use clusters to help empirically improving, it's hard to verify that these clusters are actually getting similar lemmas. So what I looked to do was create methods to automatically analogize proofs from these clusters, because then we get some data to see, well, are these actually useful? So I've created 3 new methods to do this. And some of these methods are useful because they can find proofs that brute force type searching would not be able to find. So here's the first method. So the first method is really simple. It's just essentially doing what I just showed you there and getting a cluster and copying and pasting the proof to see if it will work. So to run this, you have this lemma here, and it has this cluster in M14BG. And what you do is you just exactly do this, just copy and paste the proof in, and actually this should, on the third one, solve. Now, the reason why we've implemented this is because this does kind of show if it's actually getting good clusters up to a point, and because this is so simple, we can also do a test where we can run the simple search and then a brute force search on the simple search without the clusters to see if they're giving similar results. And for these 2 libraries, to be fair, PASS is very similar, as a lot of the tactics are very similar proofs, but we are getting a decent number of the ones proved that could be programmed with simple search compared to the brute force here. The next search we've got is just a depth first search, and this is limited by whatever you set how many the maximum number of searches. In case the cluster gets really big, there's a limit on how low the depth can go. So what this does is it goes through all the lemmas in the cluster and creates a list of lists that adhere to the tactics and the depth they're on. And then after that, it then goes through these tactics until a proof is found or the end of the list. So here would be an example proof tree, and that would be of these 5 lemmas here. So as you can see, I removed the duplicates on every line, so therefore it will go to a tree like this. So that would have had 5 intros, for example, on this tree. And just to show you the traversal, it's pretty simple at first, but it would go start off with intros, it would then try rewrite, and then it would fail there. On mul n0, it would try the next one here, which is up 12. This rewrite would succeed, and it goes to the next one trivial. So it's just a regular depth first search. The more interesting method that we've created is the context mining search. So a lot of the time, when you're doing searches, you could have a simple proof where it's induction on N, and you want it to be induction on A. So you just copy and paste the tactic, it's not going to work. So what we want to do is extract the tactics and then remove those variables and then get them from the context. But what we also do is you could have the case where you're rewriting on a lemma and it's not quite the right one. But what we do is if we do a tactic that references an external lemma, such as rewrite or apply, we will then try all the other lemmas that we cluster together with it. So okay, so let's say we're trying to prove this lemma here, which yeah, it's pretty simple. It just states that if you add 0 to a number and times the successor of 0, so times by 1, it's the same number. So we'll get this cluster here, and this will create actually a reasonably big tree. So I'm just going to show you how I would represent the actual answer it finds to this. So this is the answer it gets, which is, that's how I represent it in lists. So this basically says that we've got an induction on one variable. I keep semicolons intact so that we need to know, because they usually will almost certainly need to be applied after each other. So I keep them, so I would tell this semicolon here, it says that's 2 external rewrites on, and then that's a rewrite an internal hypothesis. So when we're running through this, we would first look at this, and we see that there's one tactic and there's only one possible variable. But if there was 2, or for example, we try it on both A and B, we'd add them both to the move list. And again, here it's just simple trivials, these are fine. And then we get to this rewrite add SN, and we look to see what cluster add SN is and add all of these rewrites here to the move list, because that's the cluster. And we would then go through this until we finally reach this plus 0n, and this rewrite goes through, and we'll move to the next tactic, which is add NS. This is a different tactic. It's just a slightly it's the S is after. And this has, again, we add these 4 new lemmas in its cluster, and we will get it, and it finally gets the rewrite on that. And we'll go to the next rewrite where we reference an internal hypothesis. And again, this is good. This we'll see that it's one of the variables that we've introduced is internal hypothesis A, and I'll rewrite on it. So we're not going to fail by rewriting maybe just if it was rewrite H, because another tactic might have just had it as H or something. And then that'll be the proof solved. I have been trying to run this on other things, on more like complex proofs, but my laptop runs this code very slowly, unfortunately. But I do have like one example of a proof that I was running on the ComSert library. So I managed to get the extraction working and everything on ComSert. So here's just one of the earlier things in one of the ComSert libraries, which is this proof. And ComSert proves it like this. And my context mining algorithm proves the same proof like this. And as you can see, this is a proof that is not at all in the ComSert library. You couldn't just find this. This has been found by using both, by using that context mining that I was talking about earlier. And I've got a demonstration of it finding this. So this is run at 4 times the speed of my laptop, but my actual desktop computer, which just runs on an i5, runs this way faster than this does. So, I mean, so that'll be it's just triangle variable combinations, really.
This is very like Hank's picture of the brainwaves.
Consciousness.
Yeah, and then that's it. And then that's the same proof, as you can see, but as before. So basically, there's a few things that I'd like to do to update it. So ideally, we wouldn't have depth first search at all, because there shouldn't be any proofs that the context mining gets that depth first search doesn't. Sorry, the other way around. I mean, depth first search gets the context mining doesn't. But there's a couple of issues that I need to add. So one thing is to see if the variable is like sometimes you introduce new variables into a proof, for example, and I've not written a check to see if it's a new variable if it was referencing a variable earlier. So that's why sometimes depth first search gets other proofs. But I'm going to add that in the future. Can you turn it back to the slide, please? Sorry. Okay, yeah. So the context mining advantages is that it can find proofs that a brute force would not be able to find. It doesn't error because of use of wrong variable names, and it makes use of clustering doubly because it then clusters on the rewrites as well. Also, I said I was going to talk about Sepia, so I'll do a quick. I've not got any proper results, but looking at Sepia and looking at the results, one thing is that it's not always that we find a cluster for a lemma. Sometimes lemmas are in a cluster by themselves. So we think that by combining the results of Sepia on the lemmas that we don't cluster with ours, we'll get the new results we get from a context mining search in additional to the results we'll get from Sepia. So we think that'd be a good step forward. So yeah, again, this is the method results. So on the simple file, which I extract everything properly, because that's what I wrote my code on. As you can see, the simple gets 62%, depth first search 66%, and the context mining gets 76%. on paths because they basically just prove stuff by doing introduction and writing exact. The context mining search wasn't as good on that compared to others. And actually, as you see, the simple search got 93, so it wasn't a very good file. So I hope to run this on ComCert very soon when I get back to get some proper results. There we go. So in conclusion, I've written an add-on that for Proof General that can automatically analogize proof based on MLPG clusters. I've added 3 new methods to do so. I've shown that at least the clustering is getting some similar numbers by using examples of the simple search. And I've shown that, more complex. Yeah, by using my more complex searching algorithms on the reduced search space, we can get new proofs that you wouldn't be able to find otherwise. And yes, the further work, I think I've already explained. That's it.
We certainly have time for questions.
Yeah.
So I guess most of the work was done by Katza previously, right?
So yeah, the clustering was done by catching. Oh, so I wrote the methods. So I wrote the methods that analogize the new proofs is what I did.
So I think tomorrow there will be a talk about Cockhammer when they evaluate on the whole Coq standard library. Have you evaluated it on something like Coq standard library so that we could?
That's the same. I'll get around to doing it.
All right.
I can get back to you with results when I've done it.
Yeah, if you do it by tomorrow, then you can tell these people that you are better.
Yeah.
How much information do you have in your context for learning? Like when you try to prove something, do you learn from other theories and then you cross validate? Or?
No, it's not learning. It's just an algorithm rather than. I'm not trying to. I don't do any machine learning in the actual context mining thing. I call it mining. That's probably a bad name. But I just get it. I query Coq to ask. Well, I use scripts to get the variables, right? Rather than. I don't guess them. I just say what are the variables in the context, and then I also do stuff like writing intros before I start a tactic to see what all the possible variable names that Coq would automatically give, for example. Yep.
Is there any hope of using timing to maybe restrict which variables make sense in that particular tactic?
Oh yes, I'm intending to do that. That is also future work. Yeah. Right now I limit because if you had for example 5 arguments and 5 variables, you don't want to try every combination of them. It's ridiculous. So yeah, I am intending to do that as well, but not quite correct.
Any more questions? Okay, let's thank the speaker again. So we have Robert Lewis is talking about adding AI to Lean.
Yes.
You can try it for a moment.
Okay, this will, my plan was to not go too long with this stuff, so there's more time to use. Okay. Cool. So thank you. My plan for this talk was to describe some experiments that we've been carrying out in the Lean tactic framework. The AI applications here have really just been side projects that we've been playing around with. So there's nothing particularly deep or novel to say. So my plan is to try to make this talk relatively quick so that we have time to go eat lunch and then go skiing. But hopefully there is something interesting in here. So I'm not introducing any novel techniques, really any novel applications. And like I said, this is all really a work in progress. Instead, we wanted to look at sort of easy or engineering-free applications. And so we wanted to see what we could get without doing too much work. We also wanted to sort of stress test the Lean tactic framework. this is a new development that seems to be quite powerful, and we wanted to see how far we could push it. But the things I'll talk about are also components of some larger projects that are just starting to get off the ground. So I'll start by telling you a bit about the Lean system, and in particular the tactic framework, or the metaprogramming framework. And I'll describe, you can barely read that, I'll describe a relevance filter for Lean that we've written entirely inside of Lean. We'll take a quick break to talk about a connection between Lean and Mathematica, and then we can do something similar, avoiding computation in Lean, exporting things to Mathematica and using their built-in machine learning tools. So Lean is a new proof assistant. New is maybe not so accurate anymore. It's a few years old. It's being developed by Leo Gamora at Microsoft Research. So Leo's coming from SMT. He's an automation guy. And sort of the original motivation behind Lean was to develop a system where you can do very complicated automated proof search in a verified way, without the potential soundness issues that you might have in C3. And it sort of developed into something beyond those original plans. Logically, Lean is very similar to COP with the calculus of constructions, dependent types, blah, blah, blah. The foundations don't matter so much for this talk, so I won't go into any details about that. I want to focus on the metaprogramming framework, and so to do that, I should talk about expression evaluation. So when you type something into Lean, you type in something like, so like 1 + 1. That is not an expression in the calculus of constructions. You need to elaborate it. You get some long, ugly expression that you would never want to write down or think about, hopefully never see. So in Lean, addition is generic over types that have an addition operator. We need to do some type class inference to fill things in. 1 is also generic over types that have unit, blah, blah, blah. You get some long expression that doesn't fit in this box. What do we want to do with that expression once we have it? Well, we need to make sure it's type correct. We need to make sure that it hopefully is a natural number. Here we're assuming that 1 is a natural. So, okay, we send it to the small trusted kernel, which will type check it, hopefully tell us that it is a natural number. Furthermore, we might want to evaluate it. This expression was written in the core CIC. There are no additional axioms. It should reduce to applications of constructors of natural numbers. So it should reduce to this, we hope. But the Lean kernel is not really designed for doing this sort of evaluation. One of the design principles here is that we should avoid computation in the kernel as much as we possibly can. Also, addition on the natural numbers is defined in unary, so if these were bigger numbers, it would just inherently be extremely slow. So, there's an independent alternative to evaluating this. Lean is a virtual machine. We can take this expression and compile it to, well, Lean VM code. Think of this as code extraction to a very, very similar language. So minor code extractions. We compile it and evaluate it in the virtual machine, which is not trusted, so we can have a much bigger code base than we have in the kernel. It will do things like replace terms of type nat with, say, GMP ints. And it will sort of evaluate it in a much more intelligent, much more efficient way. We'll get the result that we expect, something like the natural number 2 in this case. And keep in mind, the VM is completely separate from the kernel. So this isn't going to affect soundness in any way. The kernel doesn't know that the VM exists. So yeah, so they're completely separate. And in principle, we should be able to evaluate any terms in the Lean library that remain in this core fragment of the CIC, as long as you don't have extra axioms floating around. You do that, and there are various optimizations, like I mentioned. substitute native integer values. We have an implementation of arrays inside the VM, etc. And there's a lot of infrastructure built around this to make it easier to sort of see what it's doing. So if we want to execute code in an untrusted way, well, this is the situation to do it. Now, if we're only executing code, we're not proving facts about it. We're not using this code to prove things about other data structures. Well, the rules of the calculus of constructions are maybe too restrictive. In particular, we can't write unguarded recursive functions in the calculus of constructions because it would be unsound. You can prove false with a non-terminating proof of false. So this function from n to n is undefined at 0. Lean should reject this definition because maybe if this isn't unsound, then doing something very similar would immediately lead to a proof of false. But that doesn't mean that we can't execute it. I can write this function and evaluate it on 1 to 1,000, and I should get a list of 1,000 ones. So if we use this keyword meta in front of the definition, it tells Lean that this is only for the VM. The kernel should never try to evaluate this. Basically, it pushes us into some sort of, I'll call it an unsound fragment of Lean, but it's a fragment of Lean where we don't care about soundness. It's a fragment of Lean where we only care about evaluating. So why the word meta? That seems a little out of place here. Well, the motivation for doing this is to give us a tactic, to give us a way to write programs for reasoning in Lean about Lean expressions. So the tactic language for Lean is going to be this slight extension of the core logic of Lean. And the advantage here is that if you want to program tactics in Lean, you don't need to learn a new language, you don't need to use the underlying implementation language, which for Lean is C++. You use the same language that you use to prove. The entire Lean library is available. We can execute anything that doesn't have extra axioms. We have all of this infrastructure still available. And maybe most importantly to me, we can develop the automation for our theories side by side, basically in line with the theories themselves. Somehow these tactics that we're writing are core parts of our mathematical theories. They're on exactly the same level as our definitions, our theorems, our proofs. So we achieve this by exposing internal data structures in this meta framework as constants. We might have a constant type called expert, constant environment, constant tactic state, and we're also going to have, we're going to expose functions on all these types. Say 2expr will take an expression and produce, in the tactic monad, produce an expression. When we evaluate terms that use these constants in the VM will replace those terms with the underlying data types from the source code. So these are sort of placeholders for what will be found underneath. This is easier to explain with an example, and we're not going to work through the whole thing, but just for the setup, let's start at the bottom. We're trying to prove a simple lemma that says, well, if I have a contradiction in my local context, then I can prove anything. And we're going to do this using a tactic called contradiction. That tactic is defined right here. So when you read tactic unit, for now, just imagine that this is a function from tactic state to tactic state. A tactic state has a goal and some other information, and this function should instantiate that goal. So when I write by contradiction down here, Lean is going to create the tactic state object that corresponds to this declaration. We have a goal, we have a local context. We'll create that object, take this function that we've defined and just evaluate it on the tactics data generated. The hope is that the tactics data produces has no open goals, so we can find the expression that was used to instantiate the skull, and then we can send that expression to the kernel to check. So the kernel has no idea that we actually use this tactic to prove it. We just generated an expression using this tactic, and that expression is our proof. So I won't walk through how that tactic actually works, not so relevant now. But so following this approach, where we have some very basic core concepts that are implemented in C++ and exposed in this meta framework, we can then develop most of the tactics, most of the automation for Lean in the language of Lean itself. So the simplifier is a good example of this. There's a very, very small core piece of the simplifier that's implemented in C++. There's an API for this exposed in Lean. And then all of the many features, all the many extensions of this core simplifier are done in the Lean meta language. We can write processes for normalizing terms and certain algebraic structures in the meta language. You can have decision procedures for arithmetic. We even have a way in this framework to connect to external software. And maybe the most complicated thing so far was actually written early on. One of the first big meta programs written by Gabriel Ebner. He implemented a full superposition prover entirely in Lean. So again, avoiding any C++. Unfortunately, it's not optimized. Again, it was written a while ago. There's work that can be done there. But the fact that it works at all is cool, in my opinion. So right, the question is, how far can we push this? And well, one thing that we've thought of is maybe we can try to implement a sledgehammer tool. Not entirely in Lean. We can communicate with first-order provers using connections to external software. But the rest of the tool we could do in the Lean meta language. And so following the Kokemmer paper, which we'll hear about tomorrow, a lot of the sort of design is already there. We need to figure out how to translate it to Lean. And this is a longer-term project. I'm not saying that we've done this, but the first step would be to implement a relevance filter. I'm guessing most of us are sort of familiar with this idea, right? So given a proposition, we need to produce a list of declarations from our environment that are potentially likely to be of use in proving that proposition. So we need to collect all of the declarations in our environment, map over them, collect the feature set, collect the dependencies. We need to define some sort of relevance function, and then we need to find the most relevant declarations in our list. So we want a function that looks something like this. Given our target and how many relevant declarations we want, we're going to produce a list of the names of the declarations that should be relevant. Well, okay. Lean's tactic framework provides us a way to get the environment, to fold over the environment. It gives us some convenient map and array data types. So there's a red-black map, which is implemented in C++. This is a meta constant. There's not actually a specification in it for Lean. This just means it's somewhat faster to use. Lean also gives us a array type, and this is defined in actually in core Lean, not even in meta Lean. I think that meta shouldn't be there, as a state. So that it's specified facts are proved about it. When we evaluate arrays in the virtual machine, Lean will replace them with a more efficient representation in C++. In particular, it will count references